reason I want you all to sit up front is that you're going to work together. I don't want anybody doing it all. I want you to work together, which means you have to overcome your desire to surround yourself with a social space. I want you to be close. I want you to be rubbing elbows with your colleagues and talking with them. That's right. And talking with them about what you're doing. Because some unlucky volunteers are going to get up and make a presentation when you're done and tell us what you did and why. So that means you have to have worked together, and you have to have decided on who's going to be the unlucky one. Because if you don't decide, and I don't see a forest of volunteering hands when the time comes, how many of you have been in the military? How did they get volunteers in the military? They pointed at somebody and said, "You're it," and that's what I will do. Is anybody here at Des Moines last year? Will I do that? You better believe it. I hope I strike you all as somebody who means what I say. So please, A, fill up the seats in front, and B, be prepared to volunteer. Anybody sitting in a back row, except for those folks who have already told me about various problems, please move forward and fill from the front. I am not going to start until you do. Don't all jump up at once. This is paid for.
All right, we're going to turn this camera off.
Can expect. It's amazing how difficult that is. I always find it intriguing. Some of you actually paid to come hear this, and yet you're afraid to participate. Oh well, it's not my money. Okay. Severe weather forecasting. This is a multi-scale analysis workshop with some emphasis on work. First, it'll be work because you have to listen to me. Second, it'll be work because you're going to do some. Okay, I would like my first slide, so let's see if I can make this work. Naturally, no. Ah, okay. I'm going to turn this off. I apologize for the blatant sexist character of this slide. What I would hope that the females in the audience can do is make the appropriate mental substitutions. Well, you know, whatever turns you on, but... We meteorologists often take a lot of static, and many of us have a modest inferiority complex because basically in order to be a meteorologist, you're going to be wrong a lot. Being wrong a lot is part of the process. Now, what I hope is that you don't like being wrong, and we're hopefully going to do some things that will help you avoid being wrong so often, but it is something you're going to have to live with. And if being wrong is something that leaves you absolutely devastated and bleeding on the floor, you probably ought not to even try this. This is the nature of what we do. And for those of you that have heard some of the stuff on the internet that I've been putting out about probabilities, I'm hoping to sell you on the concepts of uncertainty. I want to talk about some basic principles. First, I want to see what's next. Yeah, okay, we won't get to that just yet. I want to talk to you about some very simple principles. And much of what I'm going to talk to you about is simple today, because whether you believe it or not, I'm really a pretty simple guy. A forecast, in these simple terms, is simply the combination of a diagnosis and a trend. How many of you have had calculus? Okay, a bunch of you. If you've had calculus, then these are the first two terms in a Taylor series expansion for some quantity. That is, it's the initial analysis plus the first derivative, if you've had calculus. If you haven't had calculus, please don't pay any attention to that. I can't tell you how much it bothers me when I see people focusing on progs. Yes, you would say prognosis, and especially model prognosis, is at the heart of our business. And I'm not going to tell you not to pay attention to model forecasts. But I see an awful lot of people spending an awful lot of time looking at those model forecasts and agonizing over which model to believe and all of that stuff. And they don't look at the data. They don't spend much time actually drawing lines on charts and analyzing the data. The data is the most truthful thing that we have. The models are always a lie. It's just a matter of how bad the lie is. The data, generally speaking, are truthful. Well, what do I mean by diagnosis? Well, if you're just drawing lines on a chart without thinking about it, then basically you're wasting your time. And at that point, a computer is a perfectly acceptable solution. If you're going to waste your time, let the computer waste your time. Many of us spend a lot of time wasted on computers, surfing the net or whatever. Diagnosis is not just drawing lines. Diagnosis is a matter of fitting a mental model to the data. Well, that's a pretty important concept because you have to have a mental model. If you don't know anything about meteorology and don't know anything about what are typical atmospheric structures and you don't know what the data are telling you, that's going to be an impossible task, isn't it? Now, how good is your mental model going to be? Is it going to be perfect? Not in my book, it won't be. What happens is that you are fitting a model to the data, but it's only, in effect, a hypothesis. It's what you think is the most plausible interpretation of those data. If you get new data, what happens? Quite often, you'll change your mind. The new data come in, and they say, whoa, wait a minute, that model doesn't work. That isn't a good model. I got to rethink this situation. When you find yourself doing that, then you know that you're doing diagnosis. Why does it matter? Well, we're going to talk about it. Models versus humans, a favorite subject of mine. Models definitely have certain high-quality capabilities. And I would be the last person to say that I can integrate the hydrodynamic equations in my head more effectively than the computers can do. I guarantee you I can't do that. But if you're talking about a short-range forecast, one of the things that I know about models, and you should know, is there's a great deal of uncertainty about the details. And especially in, say, the first 18 to 24 hours of those simulations. The details are, unfortunately, what matters to you if you're forecasting severe storms. Those details are critical, and I will tell you without hesitation, I can make a forecast. If you live by those models in the first 18 to 24 hours, you will go down in flames. It will leave you torn and bleeding on the floor because they can't do it. Short-range forecasts are data-driven. It puts an incredible premium on learning how to read and interpret data. When I was in cells, now the SPC, they used to call it the map factory. Did I turn that off? No. Okay. They used to call it the map factory. And the people around used to be kind of derisive about it because everybody in cells spent all the time drawing maps. Come on down front. You'll have to suffer the humiliation of being embarrassed publicly. Find seats in the front, please, if you can. They cranked out a ton of maps. We did hourly surface analysis. We did our own upper air analysis by hand. What an absolutely astonishing experience that was. To this day, I am grateful for the opportunity to have done that. Number one, I enjoyed the heck out of it. I had a lot of fun drawing maps. That's what I got into meteorology to do. The other thing was, I think I learned a lot. I learned a lot about data, and I learned about how to interpret data. I won't say I learned it perfectly, but I did learn it. So, you're going to end up drawing maps, in my opinion, if you're going to be a successful forecaster. Now, let's assume that somehow, through some mysterious process that we're going to talk about a little bit later, you have done a diagnosis. Now, how are you going to calculate a trend? Let me see if I can turn that off. There we go. How are you going to determine a trend? Well, that's a problem, isn't it? There is one way you can determine a trend, and that's, of course, to use a model. I want to show you some things to think about. And in order to do that, I want to talk about a hypothetical process. This graph describes a hypothetical process. We have a forecast quantity, I don't care what it is, temperature, humidity, precipitation, you name it. And you can see that it is a function of time. And we have observations indicated. Here's the first observation, here's a second, here's a third. So these are three observations, and the current time is right here. Here are the three data points. And you can draw a straight line through those three data points very nicely. And we call that linear extrapolation. If you're an old-time, gray-haired forecaster type, we called it the three-finger rule. You know, the front has moved 3 fingers in the last 6 hours. So in the next 6 hours, it's 3 more fingers. That's linear extrapolation. You're basically saying that what's been going on is going to keep going on. That's a way to get the trend. Now, if you have that linear extrapolation, you will make a forecast error at some point in the future. And in this particular example, the actual process, the errors get fairly substantial fairly fast, because that linear trend turned out to be inappropriate. The process is nonlinear. And I've defined on this chart, or I will define in the next chart, what I believe to be an acceptable forecast. I've decided that these are the error bounds on an acceptable forecast. I can accept it as long as the forecast is within those error bounds. And after a while, the forecast achieves those error bounds. And so this time between the current time and the future time is what I call the error bounds of the acceptable linear extrapolation forecast. And that works reasonably well for some problems and doesn't work reasonably well for others. Get this straight. It's always fun with view graphs, especially after a talk. Now, if you want to get cute, let's assume you're cute and you have this idea for a simple nonlinear model. Well, what can happen if you fit a simple nonlinear model to those three observations? In this particular example, it goes in the toilet a lot faster than simple linear extrapolation. So you can run into problems if you are trying to be sophisticated, but you haven't quite reached a certain level. Well, what we would like would be that. Okay, that's what we really want to be able to do. And you notice it's not perfect, but it's close. So we managed to do a pretty good forecast here, and it never exceeds what I've called my error bounds for an acceptable forecast. So this is acceptable for a long time. Maybe somewhere, if we kept extrapolating into the future, it would blow up. Now, how easy is this to do? Well, not very. Most of us can't do it. Now, let's suppose, again, hypothetically, that we consider all of the things that we have to consider in terms of establishing trends. Here we have some hypothetical scale of weather knowledge, and this is time into the future. Well, our knowledge of the weather at time 0 at the current time is not perfect, is it? Sometimes it's better, sometimes it's less. If we do simple linear extrapolation from the 0 time, basically that knowledge drops off pretty rapidly. How long do you think the valid time for linear extrapolation is in general if you're forecasting for supercell thunderstorms? How effective can you be extrapolating the intensity and behavior of a supercell thunderstorm into the future? How long do you think it's good to just do it by the three-finger rule? Any idea? Pardon me? Couple of minutes? Anybody have any other ideas? It depends. Okay, well that's a good answer. What does it depend on? Yeah? Well, let's pose another hypothetical situation. You've looked at 80,000 supercell thunderstorms in your long career, and in general you've extrapolated using linear extrapolation for those 80,000 supercells. How often, what probability is it that you're going to be right 50% of the time? How long into the future are you going to be right 50% of the time? 15 minutes? 30 minutes? Any other ideas? I could pick on people I know. That's fun. But it's more fun to have you volunteer. If you're thinking something and you're publicly wrong, hopefully I won't humiliate you. But if you're wrong and you speak up, don't sit up there. Come on down front. Can't sit that far in the back. Thank you. Any other ideas? Nobody has any ideas.
I would think if you've seen 80,000 supercells, you probably could do it linear 50% of the time, a couple hours.
A couple hours. Okay?
What do you mean by right?
Well, you're within some error bounds for an acceptable forecast. Some plausible error bounds. An hour? Well, I've given you the scale of the phenomenon. It's a supercell thunderstorm. But you're absolutely right, Tony. If the thunderstorm we're talking about is a garden variety little bird fart thunderstorm on a summer afternoon, how long can you extrapolate its behavior into the future?
10 minutes.
10 minutes, I hear, if you're lucky. Any other ideas? Anybody think it's 2 hours? Speak up. No. Okay. Well, how about if you're watching an Arctic front come at you from northern Canada? How long do you think you can extrapolate its behavior using linear extrapolation?
12 hours a day.
12 hours, order of a day? Yeah. So in other words, using linear extrapolation is a scale-dependent phenomenon. And it depends on the particular phenomena that you're trying to forecast. So the answer varies depending on what you're trying to do. If you're looking at large-scale features, you're more likely to be able to get away with linear extrapolation than if you're looking at mesoscale features. And there you're more likely to get by than if you're looking at cloud scale features. So this is kind of a schematic graph, and I've picked 4 hours at the time where linear extrapolation basically has no skill, but it could have been anywhere else. In fact, I could have drawn it so that it just kind of tails off. Now, if you know the climatology, climatology is typically a pretty poor forecast. But if you go far enough in the future, climatology ends up being a pretty plausible forecast. If you don't know anything about the weather and you're going to some place you've never been, what's a plausible thing to do? You go and look at the climatology of that place and you say, well, okay, in summertime typical temperatures are in the mid-80s, and nighttime temperatures are in the mid-50s. Okay, that tells you something about what to expect. Now, you've made a forecast in a sense, and if you don't know anything about a particular weather situation, climatology, in effect, is the default forecast. Climatology is a contributor to our total knowledge. If you use synoptic scale meteorologies, I show the relative skill of them as being close to 0. That may be not very real. It's probably higher than that at the beginning. But let's just assume that the basic idea is that their skill increases with time as we go towards 24 hours. If you have mesoscale models, I've indicated they add an increment to that, but they also have a kind of a spin-up time. And if people have become experienced with using them, you will find that they don't do a very good job in certain aspects of the forecast right away. It takes them a while to sort of get the hang of it. If we know everything, if you are, you've got 3 PhDs and you've been studying meteorology intravenously all of your life, and somehow you managed to know everything that there is to know in meteorology, which would be a reasonably complicated feat, let's assume this figure represents what everybody knows about meteorology or collectively. And I point out the short-range gap. And we're going to talk about that some. Let's come back to our forecasting problem then, and methods for determining trends. I will make a statement that if you have a bad diagnosis, then what often will happen is that your methods for a trend, and I'm using model in the most general term, this may be a numerical model or it may be your mental model of what's going to happen. When you start out with a bad diagnosis, you frequently wander off into some odd part of the world where things are just completely different from what's actually going to happen. That's typical when you have a bad diagnosis. Even if you had a perfect model, you knew exactly what the trend was going to be. If you start out with a bad diagnosis, you still have a bad forecast, because you're starting out in the wrong place. That seems fairly obvious. If you don't know where you're starting from, it's pretty hard to get where you're going. I had that experience last night.
Just stop at the convenience store.
Yeah. Sometimes that's inconvenient. So here we have a good diagnosis. As you notice, it's not perfect, and you have 4 different models. In this particular example, 3 of them end up looking pretty similar. They differ in the details. And then you got one model that starts out in that same place, and you end up looking rather different from the other 3. Has anybody had that experience in forecasting the weather? Yeah, that's pretty common, isn't it? How do you choose? This is where you end up struggling, isn't it? You have essentially some idea where you're starting from. I will make the assertion that if you don't know why the atmosphere got to where it is when you start your forecast, you don't have a chance. And those models, in some sense, are very strongly dependent on the details of how you got to where you are to begin with. If you don't understand the weather that's going on now, I'm going to say you're going to have a hard time forecasting. But here's the problem. The weather that's going on now may go away to be replaced by something else later. That's nonlinearity. And what's the most nonlinear thing you have to make forecasts with? Anybody? No, not the observations.
Data?
What sits between your ears is the most nonlinear thing you have to work with. But unfortunately, you got to turn it on first. It's more nonlinear than models. What you can do with your brain is take all of the information, both quantitative and non-quantitative, and use that to fit a model of what's going on to the data. And with that, you can update every time you get more data and refine how good your model is. But you have to, of course, be careful. Sometimes you go off into hyperspace somewhere and have some weird ideas because of one observation. I will tell you that from my experience, single observations can have a number of different interpretations. Once in a while, a single anomalous observation is the precursor of something very important about to happen. It is your first clue, it's your first hint that something is going to happen, and if you can recognize that clue for what it is, then you can make a brilliantly good nonlinear forecast. If you misinterpret that and you instead say, oh, that's just an observing error, and throw that piece of data away, you've thrown away the most important thing in your forecast. So before you throw away pieces of data and say, oh, I don't believe that, you got to have a reason. And if you don't know why those data are bad, or that datum is bad, you got a forecast problem. And I tell my graduate students that may be the most important thing you have to deal with that day, is solving the dilemma of the anomalous observation. Why is it there? And if you have plausible reasons to delete it because you have some knowledge, fine, go ahead and delete it. But though it frequently happens that those anomalies are the key to your forecast. And it is very difficult to do this. It is a non-trivial exercise. Well, let's think about some of the ingredients. And since this is basically for severe thunderstorms, this is my standard speech on deep moist convection. I call it deep moist convection rather than thunderstorms because not all significant deep moist convection has lightning. I know of at least several instances where huge amounts of precipitation have fallen from storms that never had a flash of lightning. They were convective, it's just for whatever reason they weren't electrified. I don't understand electricity. Okay, the ingredients: moisture, instability, and lift. They are these three ingredients, the holy triad. These three ingredients are both necessary and sufficient. Unlike most of what we know about meteorology, they may sometimes be necessary conditions, but we're not often sufficient. This is both necessary and sufficient. What happens to a tripod when you take away one of the legs? Falls over. What happens to a convective event where you take away one of these ingredients? It stops, or it doesn't happen at all. So which is the most important ingredient? Trick question, right? There is no most important ingredient. They are all three necessary. If you know me, you will know that you do not use the word trigger in my presence, because I'm going to jump on you in an ugly way. Why? Well, most people use the word trigger to refer to lift, as if it is somehow always the missing ingredient. Not necessarily the case. Not at all. If you have two of the three ingredients, you may very well have important weather events of one sort or another, but you won't have deep moist convection. So lifting is not a trigger, in my opinion. It's a mechanism for initiation, but trigger has some connotations I don't like. Okay. For severe weather, what are the ingredients? Well, here's where we have problems. We know how to get deep moist convection. We know what the basic ingredients are, and we know them to the extent that they are necessary and sufficient. When we come to hail, strong winds, and tornadoes, we do not know with great clarity both necessary and sufficient conditions for these. So it's difficult. We have some ideas, and I could go on at length about them. I'm going to choose not to do that in the interest of saving a little time. But some of the things you might want to think about: dry air aloft, helicity or some kind of wind shear in the wind profiles, and a bunch of stuff like that. Surprisingly, I think we know almost nothing about what makes storms into hailstorms. We know that you have to have a strong updraft in order to have hail. You can't get chunks of ice the size of baseballs without a strong updraft. But the problem is that a lot of storms that have strong updrafts don't produce any hail, and we don't know why. So that's a little frustrating. Well, I promised multi-scale analysis, so I wanted to talk about synoptic scale processes. Synoptic scale processes is the scale that deals with extratropical cyclones, the highs and lows that go across your weather map every day. The scale of them is thousands of kilometers across, And these processes last, by the way, you notice I said kilometers, not kilometers. Do we say centimeters? Do we talk about kilograms? Okay, I have a thing about these petty inconsistencies. At any rate, thousands of kilometers across, they last for several days. That's what I mean by synoptic scale. And it turns out that on that scale, in space and time, in mid-latitudes, there's essentially only one process, the extratropical cyclone. That's all there is. It is generally thought that extratropical cyclones, the highs and lows, carry on a process of what I would call stage setting. They create the conditions for convection. They bring in moisture. They alter the stability. And those two things together make it possible for storms to happen. But by themselves, extratropical cyclones normally do not initiate thunderstorms. It is commonly said in forecast discussions, well, we've got a shortwave trough coming and PVA is going to trigger thunderstorms. Well, that hits about 6 of my favorite pet peeves. Most of the time on this scale, the vertical motions we're talking about are too weak, and it would take a day or more to lift a parcel to the point where they could actually participate in deep moist convection. It's too slow. So we have to look elsewhere for the sources of lift. Okay. And synoptic scale lifting basically occurs over big regions. And we don't normally see regions the size of a state flash into cloud. What happens is thunderstorms, deep moist convection gets started at essentially points, which isn't consistent with a source for lifting in synoptic scale ascent. So we have to look elsewhere. Synoptic scale processes do something very important for us, however. They provide a backdrop for mesoscale processes. Mesoscale processes have a number of properties, and I could go on at length about them, but mostly what I could go on at length about is how little we know. I will say this. Mesoscale processes depend critically on the synoptic scale environment. Who's been involved with lake effect snow here? Anybody? Okay. How many people have experienced front range snowfalls in the Rockies? Okay. How about, what do they call them? Coastal fronts. Okay. These are mesoscale processes. Their variability is on the order of tens to perhaps hundreds of kilometers. And their time scales are less than a day, perhaps down to a few hours. For those of you that have experienced lake effect snow, does it matter which way the wind is blowing synoptically? You're damn right it does. If the wind changes by 20 or 30 degrees, the lake effect snow may quit, or it may happen somewhere else. So the synoptic scale environment is a critical factor in determining where and when mesoscale processes are needed. Mesoscale processes represent intermittent phenomena. They don't happen all the time. How many times do you look at a weather map and see no highs and lows? Synoptic scale processes go on all the time. Mesoscale processes are intermittent. And the reason they're intermittent is that the synoptic scale processes are setting them up. And they only happen when they're needed. So let me ask you a kind of a philosophical question. Who's in the Weather Service? Okay. You've been told that the future in the Weather Service is mesoscale meteorology, right? And you're going to quit doing that synoptic scale stuff. Go ahead and let the models take care of that. And you're going to focus on the important mesoscale stuff. Well, I will tell you without hesitation that I think that's just unmitigated baloney. And I'm trying to censor myself. If you don't stay involved with synoptic scale meteorology as a forecaster, you're never going to get mesoscale right. It's hopeless. You got to stay into it, and you can't let the model take care of it for you. You can't. It's like you put your plane on autopilot. You know, you're definitely going to go down in flames if you never take it off of autopilot. There are going to be times when you need these things, and if you're not involved with it every day, doing it every day, thinking about it every day, what happens to a skill you don't use? You lose it. If a pilot never flew a plane, except in the odd emergency now and then, would you be confident to get in that plane? Would you trust your life to that guy? Not me. Okay. So, models, MOS, various kinds of objective forecast methods exist. If you're a forecaster, you can go ahead and just let meteorological cancer be terminal. What do I mean by meteorological cancer? Those of you in the Weather Service know about it. That's where you just take the automated product, put it out there without any touching, without any manipulation by human hands, and you put your feet up on the desk and, you know, do the crossword puzzle. And there are folks who do that. And I think that's a travesty, but you can get away with it. As I say, a good quality synoptic scale forecast is essential. Talk about mesoscale processes. Very important to the initiation of deep moist convection, and they may very well accomplish some of the stage setting. There is tremendous horizontal and temporal variability in meteorological variables on scales we don't see very well. You get hints of that in the surface data. A lot of the processes going on in mesoscale we don't know diddly about. How many mesoscale experts do you think there are? Well, I don't think there are any. I don't think anybody understands mesoscale meteorology. If we're going to become meteorologists on the mesoscale in the Weather Service, I keep asking, where's this knowledge we're going to plug in? They keep talking about the new mesoscale knowledge. I'm damned if I know any. By the way, if anybody says they're an expert, you know right away they don't know anything. You can put that one in the bank. Somebody once told me an expert is an X is a has-been and a spurt is a drip under pressure. We are just students. All of us are just students. We're all trying to learn. Some of us have worked all our lives to find out how little we know. Some of us resent people who come by their ignorance the easy way. We've worked hard. Mesoscale processes are poorly observed, therefore poorly understood, therefore poorly forecast. On any given storm chase, or spotting exercise, or anything having to do with deep moist convection, the mesoscale processes may be the factor that determines the outcome of the event, and we're basically guessing for a lot. Unlike on the synoptic scale, there are many, many processes on the mesoscale. The synoptic scale, one process, the extratropical cyclone, reasonably well understood. Mesoscale, man, it's lots of stuff. We'll talk about some of that stuff. Unseen variability, I talk about all of the things that are happening we don't see. How do you deal with it? Well, I don't know. Fronts and dry lines are important mesoscale processes. Outflow boundaries are important mesoscale processes. And of course, there's gravity waves. If you don't know what's going on, it must be a gravity wave. Well, I don't find that useful myself, but you know, there's people who made careers studying that stuff. I could say a lot of really nasty things, but I won't go on that line. Let's look at some slides again. I want you to begin to think like mesoscale forecasters, whatever that might mean. Here is a situation. This is at 12Z. Don't worry about the date. Here's a front analyzed by my colleague, Dr. Maddox. And you see various kinds of weather symbols here. This is drizzle. These are rain showers. Here's heavy drizzle. I never used to think heavy drizzle existed, but I was on a storm chase once, and we got into a really wild heavy drizzle storm near Amarillo. It's kind of strange. Okay, here's this situation in the morning. It's basically 7 o'clock in the morning. Okay, what do you think is going to happen to the intensity of that front? What do you think is going to happen? Why? Precipitation behind it. And what's going to happen ahead of it? Okay, so it's morning. The sun is just barely peeking over the horizon. It's raining and drizzling and cloudy on the cold side of the front, so you just made a mesoscale forecast. Let's see how well it turned out. Congratulations. Okay, the front became more intense. By 0Z, it was very cold back here. It's still precipitating on the back side. Down here, it's warmed up. Now, was that so hard? There are some things we can do. Here's another example. Here's another frontal boundary. This is again at 6 o'clock in the morning. 7 o'clock in the morning. What's going to happen to that boundary? Is it going to get stronger or weaker? Why? Well, that's a thought. Well, there's drizzle, fog, and stuff in the warm sector. How many of you been to West Texas?
It's going to warm up. Dry air.
This is dry air, isn't it? If it's dry air and clear skies, what's going to happen? It's going to get hot back there. Is this a front? It's a boundary. At 6 o'clock in the morning, it sure looks like a cold front. But is it a cold front? It's probably a dry line if you're familiar with that. A lot of people analyze these, used to anyway, as cold fronts. Well, if we go to 0Z, lo and behold, it's gotten hot back there. And in fact, the frontal gradient has changed sign. Well, we just made a highly nonlinear mesoscale forecast. And it worked out, more or less. It is possible to do this. Now, I asked the question, is it a front or a dry line? Does anybody care? Does it matter to you as a weather forecaster whether you analyze a boundary correctly? Yeah. Why? Go ahead and speak up. It's okay to be publicly stupid. It happens to me all the time.
We're going to have different influences.
Okay. If you misunderstand the nature of the phenomena that you're analyzing, what are the chances you're going to forecast them well? It makes a heck of a difference whether it's a cold front or a dry line. What kind of air do we typically find on the backside of a cold front in terms of static stability? It's stable. What kind of air do we find on the backside of a dry line? It can be nearly dry adiabatic lapse rates. Very unstable. Well, do you think that matters to what's going on along that boundary? You're damn right it does. The atmosphere knows about those things, and if you don't get them, the atmosphere is going to bite you. It's the way the atmosphere is. Yeah, there it is. It's one of the problems with being a wanderer. I always took Dion seriously. Let's make another forecast. Okay, this is 0Z. It's August. What do we have here? This is an 850 millibar chart. By the way, how many people know about hectopascals? Okay, I would argue that the science of meteorology hasn't been advanced 1 millimeter by changing from millibars to hectopascals. So I'm going to keep using millibars. I'm sorry. All right, what do we have here? That's a low-level jet. And if you can read it, it may be a little hard to read in the back. We've got wind speeds maybe 20 knots. This is a 20-knot ice attack in blue. Okay. Now, for those of you who are undergraduates or senior level or graduate students, there is a process that explains the low-level jet in terms of coupling and decoupling with the surface by means of turbulence in the boundary layer, right? And the low-level jet in the afternoon, in this case, is experiencing a lot of friction, isn't it? And this simple theory, and it's really simple, makes the assumption that when the sun goes down, that turbulence in the boundary layer diminishes because it gets very stable when the air near the surface cools. And so the winds aloft no longer feel the surface. So to them, it's like somebody hit a switch and turned off the friction. And at that point, when the atmosphere no longer has friction, it's out of balance. And the atmosphere will respond. And one of the things that the atmosphere will do is the winds will speed up. And for those of you that know what I'm talking about, notice the winds in this case by 0Z are going from high pressure, or in this case high heights, to low heights. So they're crossing the contours from high to low. That's typical in a situation with surface friction, isn't it? Well, we make the prediction if you turn off the friction, it's going to change the direction of the winds, as well as speeding it up. And we can forecast that the winds at 12Z at the next sounding time will be much closer to parallel to these contours. because you've turned off the friction, and they'll be faster. What will that do? You see here the red lines are isotherms, right? Lines of constant temperature. At this point, the wind is blowing parallel nearly to those lines. If the wind changes direction, it's going to be blowing across those lines. We call that warm thermal advection. And that turns out to be physically important for various things. So we make a prediction by 12Z, the wind will strengthen and turn to the right. Voila. Now this is the simplest of simple models to explain low-level wind flow, and there are many other factors to worry about. But using this simple conceptual model, you're able to make a nonlinear forecast. You're not simply extrapolating what's going on now into the future. You're saying, I'm going to take what I know about physical processes and turn that into a weather forecast. That's a difficult task. I've given you the simple answers, the simple problems. Here's a case of a mesoscale convective system, perhaps meeting mesoscale convective complex criteria. I really don't care. In Missouri, covers a big part of Missouri, southeastern Iowa, and western Illinois. On there we have the Raywinson locations in 1982. In their wisdom, the National Weather Service has seen fit to shuffle the deck of Raywinson locations. I would go into a long diatribe about that, but I won't. At any rate, this is what they looked like in '82, and you'll notice that the whole mesoscale convective system fits neatly in between the soundings. So how much mesoscale analysis are we going to be able to do using the Raywinson data? None. And this is pretty typical. Now let's ask ourselves, all right, in this case it fit in between. Let's suppose we shift it eastward 100 miles, and then Peoria here is right in the middle of that mesoscale convective system. What do you think about that situation? Is that better? Why not? Basically, you lost the data from that Raywinson. That data is garbage. I could go into a long discourse on what it takes to resolve the structure using data. One sounding does not resolve the structure. And what you see is not representative of things that are on the order of 400 kilometers apart. It's representative of what's going on at that spot in a very complicated mesoscale system. So in effect, if you're unlucky enough to have one of these things sitting over your sounding site, essentially you can't do much with the data because they're unrepresentative, no matter what they show. Here's a figure taken from a wonderful paper by Ted Fujita in the 50s. They had, in 1953, a network of special surface sites, not sounding sites. And he took all the data from all those sites and laboriously, by hand, turned them into these beautiful analyses of the structure of convective systems. How many of you have seen this before, or something like it? Okay, many of you. Let's stop and ask ourselves some questions. What is a thunderstorm for? If I'm a thunderstorm, what is my purpose in life?
Mixing the atmosphere, stabilizing.
Stabilizing, mixing. Why is that necessary?
The atmosphere's out of balance.
The atmosphere has created an excess of heat, both sensible heat and latent heat, at low levels, and it's my job as a thunderstorm to take that excess heat at low levels and spew it out into the upper atmosphere, and to take the excess cold and dryness in the upper atmosphere and spew it out at the bottom, thereby mitigating, removing the processes that called me into existence in the first place. Being a thunderstorm, my goal in life is to kill myself. And every good thunderstorm, like a kamikaze pilot, wants to go out there and die. And in fact, if they do that, they've done their job and they're no longer needed. So what does that say about what's going on underneath a bunch of thunderstorms? At the surface, what are you going to see, typically? No, not at the surface, not unless you're talking about seismic waves. Okay, the surface, you don't have very much up and down draft. Cooler, drier air. That's what a thunderstorm does. And what happens when you cool the air and dry it? What happens to the pressure? For those of you who are students of meteorology, the pressure goes up. So you find underneath a complex of systems, you have high pressure, and the air is cool and relatively dry. Now, if we're talking about our little summertime, ordinary garden variety bird fart thunderstorm, how much cold air does it spew out? Well, I hope you get by my tone of voice that it's not going to be a lot. And if that's all you get is one little puff, and it kills itself and is thereby fulfilled, you're going to get a little bit of cool air. And what's going to happen on that summer afternoon when the sun beats down on that cool air? It's going to warm up, and an hour or two later, you may not even see it. You wouldn't see it. Also, how big is that pool of cold air? It's only a few kilometers across. The typical surface sites are about 100 kilometers apart. On the average, you're not going to see that little puff and its effects. And if you do, you're only going to see it at one point. And it's going to look out of whack with its surroundings. But here we have systems that are big enough to affect more than one station. Now, how many of you have mesonetworks in your state? A few. Oklahoma has got one. Texas doesn't. It's nice, but it doesn't really affect your job as a forecaster or diagnostician. You still have to go in there and tear apart the data and try to understand what it's showing. Now, most of us don't have these networks, and we aren't going to see all of this detail, right? So we find ourselves in the position of the proverbial three blind men and the elephant, don't we? Okay, we might get one sample or two. And if you're in one part of one of these beasts, you may think it's a snake. If you're another part of it, you may see a tree. It looks like a tree. But you don't know. You don't know where you are because you only have a limited sample. We are in that position as diagnosticians. Well, that sounds pretty hopeless. But it isn't that bad. It isn't quite that bad. Because we had people like Ted Fujita and other geeks who go out and look at the weather in a research mode, if you understand the concept of elephantness and you get your blind sample, you might well, in fact, correctly recognize that it's some kind of critter. And you're better off if you recognize it's a rhinoceros, but it turned out to be an elephant, than if you thought it was a tree. You might get quite different results from this experience if it's a tree rather than some large critter that you're sampling. So, what does that say? Well, what it tells me is that in order to do our best possible job, we have to have a toolkit that includes everything you can put your hands on to tell you about the concept of elephantness. If you're going to do this job, you can't get by in school or in whatever other capacity you're learning with the bare minimum in order to get a C. Minimalist forecasters aren't worth a flip. You got to understand as much as you possibly can. And even then, you know you're not going to be perfect. Okay? See, I have about another hour. Yeah. Yeah. When do we want to do a break? Well, actually, I'd rather do it more or less now. Can we do that? Or is nothing ready?
I don't think it's ready yet.
All right. Well, we have, all of you have the exercise and your colored pencils? Okay. Let's drag them out. Now there are some directions on there. Hopefully most of you can read the directions. They are fairly simple directions, and I will tell you in advance that this exercise is designed to give you the absolute minimum of information. So don't gripe at me about what's not there. I would like you to work together with people near you, even if you don't know them, and talk about what you're doing, decide who's going to do which one. I would rather you only did one of the 3 maps. Yeah. And let somebody around you do another one. We have probably 45 minutes to play with it, including the break. If you have to take a break, as far as I'm concerned, if you got a biology problem, go fix it and come back. Do the whole... somehow among yourselves decide who's going to do which ones of the 3. Do one of them, but I'd like to make sure that somebody does each one of them. Then I'm going to pick an unlucky soul or 2. 3 exercises. In fact, I'd like to get 2. And what I would like you to do, if you volunteer, is stand up and show the studio audience and all the folks at home exactly what you did and give a brief explanation of why. And when I say brief, it has to be very brief. So those of you who are courageous, if I point at you, by the way, when we get to the point when nobody volunteers, which is almost inevitable, if I point at you and, oh, there's a volunteer. Okay. That's very good. We have some. If I point at you, if I'm forced to do that, and you're not at least an undergraduate student, then you're off the hook.
Make sure I'm clear on the ground rules here.
Yeah.
You want us to...
We need to get going fairly soon. So the first exercise is the one with the least data, where somebody was forced to make a lot of guesstimation. Do we have a volunteer for the first one? Okay. If that person foolishly will come forward. And we need another one who did that exercise. All right. Wonderful. I hope to have lots of volunteers from among the student contingent. Yeah, you can just stand up front and kind of hold it up, and of course it'll be impossible to see, but that's advantageous.
I'll go over you. A lot of you guys were kind of talking about complaining. It was a little bit messy. It was fun. It was a good one. It's a good choice.
Okay.
Got a basic the pressure analysis that we've done here. You're going to kind of see a little bit of a hint of a warm front. It's not big scale warm front running through this area. All right, you guys over here, I'm kind of blocking out. You've got what we're going to see is a supercellular meso circulation. Right down here would be in northeast.
One of the things you find out in meteorology is that you have to learn geography on the side. If you're not a map freak, you're going to have problems.
Right in the middle of the paper here. You're going to see it's associated with your conceptual model, your associated meso models that are on each side of the meso.
Can you indicate where you put those isotherms and why?
The isotherms, yes. I put the 60-degree isotherm along the outflow boundaries of the mesohymes and overrunning the warm front. It's not particularly warm front. The reason is that because you see most of the time the moisture come up along this circulation and feed into the mesocycle. So I'm going to look at the 60-degree point for that. You can't put your temperature, 60-degree temperature on the wrong side of that. It doesn't work. So it is, in my opinion, it's pretty hard to say what exactly what the 70s and 50s were after for something too.
Yes, I know.
It's going to be pretty hard to
Yes, it is. What about the dew point?
I put the 60-degree point right up along what I thought we thought the outflow boundary from the mesohyme point.
Okay.
The mesohyme is behind the mesocirculation. And that pressure would be back there, and that was a mess.
Okay. I'm going to cut you off in the interest of time. Don't go away. Our other volunteer?
We have real close to what you have. We also had that meso low in northwest Alabama, northwest Missouri, northeast Alabama. One thing we do disagree on is our dew points. We carried our dew points up farther north, up along the warm front boundary because all the reports are fogged. We figured the dew points would be real close to the temperature. And we thought the 60-degree line would be around where the warm front was. So we carried our dew points a little bit farther north, not associated with the outflow.
I noticed that you have a something here that he doesn't.
Our group. We were going with front either up here or front more like what he had, and within our group, and came up.
So there were some differences of opinion.
Yes.
Gosh, that's terribly unusual, isn't it? Okay. Well, thank you, gentlemen. You may take your seats. Anybody have any wildly different solutions they want to get up and advocate, thereby trashing what these guys just did? No? Okay. Well, what I'm going to show you is the gospel according to Maddox. Bob Maddox did these analyses, and this is his version of truth. And one of the things I want to emphasize about this whole exercise is that truth is, in essence, in the eye of the beholder, except that you have to look at the atmosphere as the final arbiter of truth. Well, this has been analyzed as an outflow boundary, and we have analyzed a quasi-stationary front across the region. This is northern Georgia, Alabama. How many of you noticed, where is it? It's kind of hard to see. These are all hard to see. Yeah, there it is. What's this symbol? Freezing drizzle. How many of you know how to read those symbols? Okay, some of you do. That offers you a rather interesting clue about what kind of temperatures we're dealing with. So if you had, 60-degree temperatures up here, that's perhaps not a very good analysis, or not a very good guess. Sometimes the clues in the data are pretty subtle. This is a rather interesting system, and Maddox's analysis is what it is. Inevitably, there are differences. If you were looking at a situation like this, what time of year do you think you would be looking at? Well, let me back up. One question. What is the synoptic scale mid-tropospheric flow for you meteorology types, say at 500 millibars?
Northwesterly. Yeah.
Why is it northwesterly?
Wants to go parallel to it.
Okay, this quasi-stationary front represents a thermal boundary, if you believe the gospel according to Maddox. And quasi-stationary fronts typically are aligned approximately with the mid-tropospheric flow. If it is northwesterly flow, what do you think the future of this convective system is? Is it going to be quasi-stationary and sit there and rain for several hours and not move very fast? Why not?
Perpendicular radius.
If the mid-tropospheric flow is from northwest to southeast, doesn't that tell you something about which way the system is moving and which way and how fast it's likely to move? What if this outflow boundary were oriented more parallel to the mid-tropospheric flow? What do you think it would do then? Then it might be much more slow moving. When you have an outflow boundary that is roughly perpendicular to the mid-tropospheric flow, this thing is going to haul ass. You're not going to get heavy rains in the sense of flash floods. It may rain like mad for a brief time, but it's not going to be a flash flood case. What's this? We got pressure falling rapidly here. There used to be remarks in the surface observations. I think they're tending to go away, I'm sorry to say. That's another one of those benefits from observations automated. Here's pressure rising rapidly. Okay. What's this? No, a supercell is a thunderstorm. This is probably 50 kilometers or more in size. That would be the biggest thunderstorm on record. Is that a supercell? What is that thing?
Synoptic scale low.
It's a low pressure. Is it a synoptic scale low? It's a meso-low. If it's a meso-low and you've got forecast duty in Atlanta, you're at the forecast office in Atlanta, are you browsing through the crossword puzzle book? I hope not. What are you thinking about? What are you worried about? What kind of thunderstorms? How severe? Well, we've got a mesoscale convective system. We got winds. In fact, this is actually a symbol for a severe thunderstorm with hail. We got strong winds. Okay? So you have to be worried about hail. You have to be worried about strong winds. And with this kind of structure, you also have to be thinking about the possibility of tornadoes. But you're not thinking about flash floods, because this is a fast-moving squall line. Okay, there are many other questions we could go through on this one. I love this exercise. Anybody have any idea what time of the year this is? Is it May spring or is it March spring? Whoa, differences of opinion. I love it. Who said March? Who says May? Okay, a May person, not Al. Why? Tony?
More stationary nature of the stationary front itself was more.
They don't have stationary fronts in March?
Not as often.
Okay, not as often. Okay. All of you March people, why are you March? You think Tony's full of crap? Who wants to stand up and tell us why Tony is full of crap?
Implying that he is full of crap.
I'm not implying anything. Yeah, why is it March?
With the report of freezing drizzle.
Yeah, how many freezing drizzles do you get in May? Yeah, right there. Okay, well, it's not impossible. Okay, if it's March, what time of day is this?
I would guess early in the morning.
Why? Why early in the morning?
Well, MCSs tend to form the overnight hours.
Okay.
Stronger jet. This March, you couple that with the freezing drizzle, which often gets done in the morning. Because, March is late enough.
Okay. Any other opinions?
What did he say?
He said early in the morning. And he said it was that because mesoscale convective systems typically get going overnight. And a few other things. Any other opinions?
I say early evening.
Why?
It looks like the mesoscale convective system has just gotten started up. That doesn't look like it's that old.
Okay. That's a good point. Awful strong winds, severe thunderstorms. MCSs frequently are petering out in the morning. But wait a minute. Does the answer vary depending on whether this is March or May? Why?
Heats much more quickly in May.
What's characteristic of May? Let's assume this is a really bizarre situation in May where we actually are cold enough for freezing drizzle. What's characteristic of convective systems in May? In the deep south? Are they typically nocturnal? Of course, this is a bit atypical, isn't it? If you've got northwesterly flow pushing a convective system, what kind of processes are going on in mid-troposphere? Do you suppose there's a shortwave trough embedded in that northwesterly flow? Okay. If that's the case, with strong dynamics, it may not matter very much what time of day it is. When you have strong forcing on the synoptic and mesoscales, situations are much less dependent on what time of day it is. So it's much less clear from this limited information we gave what time of day it is. Okay, there are many more things you can do to make inferences, but it's important to understand that your set of expectations about the evolution of this system depends on what time of year it is, what time of day it is, what the synoptic situation looks like. We're trying to go the other way and try to infer those things from the limited information we gave you. When you're dealing with it as a forecaster, you take that information and use it. We have intentionally made these exercises difficult by hardly giving you any information at all. You sit there in an office or looking at the internet, and you got a blizzard of stuff coming at you. And a lot of times you don't look at the right things. You're not asking yourself the right questions. This exercise is designed to make you ask, well, I want to see what those charts look like. Okay. Next one. Who wants to volunteer for the next one? This is the answer. This is the answer according to Maddox. That's all I'm going to give you. Who wants to do the next one? Among you students, I better see some hands. All right, there's one. Good man. Another one? For the Oklahoma-Texas thing? Who's a student? Get your hands in the air. Come on, I know who you are, or somebody knows who you are. They paid for you to come here. Jeff, you want to give it a try? Good. Okay. I knew I could count on College of DuPage. The rest of you ought to be embarrassed and humiliated.
All right, well, I just want to warn you that I'm not a good Vanna, but I'm going to do my best impersonation.
Okay. Please.
All right, we started off with finding the low and setting up. We found one mesoscale high and possibly one below. It was really hard to place the fronts because of the fact that we at least identified two outflow boundaries, so we focused on that more. The first one, of course, is above the low, which is situated, where the hell is it?
That's the Red River.
Yeah, I got that.
Okay.
North Texas, southern Oklahoma, centered, that sort of thing. The high is up near Tulsa, or the meso high that we found was up near Tulsa. A big area of, or a big outflow boundary to the north. We were kind of thinking that one was starting to set up to the south. It appears to be a bit smaller. The circulation is a little bit weaker, but we figured with a 45 knot wind, something was going on. The front, we found two fronts, or identified what we think would be two frontal boundaries. First one heading north along the leading edge of the outflow boundary, and the second one heading south along the leading edge of what we think is the second outflow boundary. So,
Okay. Jeff, you want to tell us what your solution was?
Well, we found the one high seems to be in the north part of Oklahoma. The cold front, the low seems to be, I'd say, the east part of the Red River, probably around Childress. Cold front extending south. It appears we've got thunderstorms tracking with relation to here, and there's also thunderstorms forming in the northwest of the Panhandle. The outflow boundaries were hard to find. I believe there would be one in front of the front with the storms that are associated with here. Also, there's some very unsteady pressures and some pressure falls in western Oklahoma. The rest of it seemed to concur pretty much with what he found. It wasn't that difficult to really do.
Okay. Any wildly different alternatives that anybody has the nerve to talk about? Okay. Thank you, gentlemen. And we go to truth. Okay. I love this one. This one I could talk about for an hour or two. This is a big outflow boundary and a really large mesoscale high pressure center associated with all the cold outflow. And you can see they have a thunderstorm with hail at Tulsa and pressure rising rapidly in southern Oklahoma, central Oklahoma to Oklahoma City, pressure unsteady. We have a meso-low here along this intersection between boundaries. And according to Maddox, this is an outflow boundary, not a front. Sometimes it's difficult to tell the difference. What's a way that you could tell the difference if you had more information? Satellite might be helpful. I can think of something that would be even more helpful.
Radar.
No, not radar either. Not a sounding. Something really simple. What if you had been analyzing the weather charts 12 hours earlier? And in fact, had been looking at the weather all of this time? You'd know where the synoptic scale fronts were before any thunderstorms got going. And then you'd have a lot less difficulty. You would have been taking advantage of what? All you weather service guys? Continuity. Okay, now continuity has to be tempered with the fact that your model changes from time to time because the atmosphere changes. You can't force continuity where it doesn't belong. You got to look at the data and always be reinterpreting. Well, let's assume that Maddox is a godlike figure, and this is in fact truth. That's probably not a bad assumption. Okay, here's a severe thunderstorm in central Texas. A 45 knot sustained wind, a severe thunderstorm with hail, wind shift, pressure rising rapidly, continuous lightning. There are two outflow boundaries, this one and this one. Which one is older? Which one's been around longer? Why? The high is more set. Basically, this high is deeper, bigger, more cold outflow. It's older. Storms have had time to put out more cold air. This one is probably younger. Let's suppose you're the duty forecaster in Fort Worth. What are you thinking about? Well, you got a problem, don't you? You got a severe thunderstorm. I guess that's Mineral Wells. You got a severe thunderstorm at Mineral Wells. What if it's the beginning of your shift and you just walked into it and the guy who briefed you before you started said, yeah, we got some stuff going on, but I'm going on annual leave, and so I haven't looked at it very much, so I'm out of here. Goodbye. Okay, for you guys in the weather service, did you ever get a briefing like that? Did that ever happen to you, something like that? Okay. Did you ever give one like that? Okay, I hope not. What about Oak City? You're there at Oak City. What are you worried about? Well, in order to know what you're worried about, there's a couple of things you need to know, right? What time of day is it?
Night.
Why is it night? Okay, well, can't you see lightning distant in the daytime? Yeah, sometimes. Okay, what time of night? Is it 9 o'clock or 4 o'clock in the morning? Why? Hmm? Hmm?
Too many observing stations looking at cumulonimbus building southwest and northwest. There's a lot of visual.
This is Lubbock. These guys can see a CB distant. How many of you been to Lubbock? How far distant can distant be in Lubbock? On a good day, those CBs could be over the mountains in New Mexico. People who are accustomed to year-round deep moisture can't possibly appreciate how far distant really is in West Texas. Okay, well, so what time of day is it?
It's a low cloud bank, so you've got to see something that's not illuminated by lightning.
Okay, so maybe it's morning. or near sunset? Which would it be?
Near sunset.
Why morning? Well, we got two diametrically opposed answers. That's good.
Mature mesohighs they'll be remnants of long-lasting convection through the night.
That's a reasonable answer. Typically, a meso-high associated with a convective system is that's that big. You're going to see that in the morning, not in the evening. For evening, why would you say it's evening? Did you give up? Quit?
The light being visible down in southeast Oklahoma. Light being visible from distant station I'm looking at. It must be Muskogee or something like that.
Where? This guy? That's...
Down further south.
Oh, here. Well, you couldn't see lightning in the morning? You could only see lightning in the evening?
You don't very often get CVs distant west of Lubbock.
Okay. Well, that's a really good point. I'm glad you mentioned that. Let's just suppose for the moment that this is 8 o'clock in the morning or 7 o'clock in the morning. Sun's just coming up. If you got a CB distant west of Lubbock, what does that tell you? Why? You never see that? Not usually. So if you do see convection in the morning off the mountains of New Mexico, what does that tell you? There must be a heck of something coming at you. So if you're the duty forecaster in Lubbock, you're aware all of a sudden that today is probably not going to be an ordinary day. Well, let's suppose you're the duty forecaster in Amarillo. What are you thinking about for today? Remember, you got that powerful ass-kicking shortwave coming at you. So, what are you thinking about? You've had an outflow boundary south of you. Okay, is that, what does that tell you? Well, one of the things about outflow is that outflow air is stable. So are you out of the woods? What's a possibility? Okay, that boundary could be the focus for new convection developed later on that day. So all of a sudden, you've become very worried about what's going to happen to that boundary. Let me ask you, the action area is all at the leading edge of this thing, and there's nothing going on here. Rain has ended, you got some showers and so on. If this happened to be in the morning, what is going to be an important question for you to answer about the behavior of this outflow boundary? Okay, but what are you going to need to know? Cloud cover, somebody said. I'd say that's really important. Let's suppose you got a big bunch of anvil debris sitting over here. That may affect how much heating is going on. And if it clears rapidly back here, what's going to happen to this air? It's going to warm up. Okay. And if it warms up, this boundary might retreat. And in fact, the boundary may scoot up into northwestern Oklahoma somewhere. A lot of things to think about. And of course, you got to imagine what's going to happen when whatever it is that's causing CBs on the mountains in New Mexico starts to affect things. What's that going to do? Well, one thing you're going to have is a return of strong southerly flow. That reminds me, a factor of some significance is what's going to happen to this. This is apparently a younger system, right? So it's still cranking and putting out nasty stuff, what's going to happen to this meso-high? If it stays there and remains in place and is strong, what's that going to do to moisture return up the lee slopes? It's going to cut it off. But if this thing collapses in the next 2 hours, goes away, then that opens the door to the possibility of a rapid return of moisture up on the high terrain of West Texas. Lots of things to think about. What about, remember I started out with our duty forecaster in Fort Worth or Oklahoma City. What are they worried about at the time of this map?
High winds.
High winds, well, that's plausible. Can you be more generic? More general? Well, both Fort Worth and Oklahoma City have to deal with something, don't they? What? They have to deal with severe weather. What kind of severe weather? High winds, hail, any possibility of tornadoes?
On the intersection of the boundary?
Yeah, it looks like a plausible thing. What's this, a meso-low? You may very well have some serious things going on in this vicinity. If they're not happening now, they may be happening in the next hour. So you got to worry about that. Anybody worried about floods? Don't forget about floods. You get all wrapped up in severe weather. What did this mesosystem do all night? It's been raining all over Oklahoma and perhaps even part of the Texas Panhandle. So you've got antecedent precipitation. It's rained in this area. If new stuff gets developed on this boundary, you could very well be raining on top of already saturated soils and have a serious flash flood problem. Lots of things to think about. And unfortunately, in this case, well, in this case, we got a lot of samples of this system because it's big. Do you think the structure is this simple? No, if you had a mesonet, which we didn't have back a few years ago, you wouldn't see all of the structure, and you don't see very much structure in here. It all looks kind of smoothed out. That's a necessary thing that we do in order to come up with a plausible analysis. There may be all kinds of structure in here you don't see. A lot of times that structure is going to be important and you have to guess. But you have to go on what you think you know and sort of typical behavior. And you have to think about the situation, the time of year, the time of day, many times the same questions. And what's going on now may not be going on later that day. What's going on now may be gone to be replaced in a convective system with a whole brand new kind of convective system. But the rules have been changed by what went on previously. The mesoscale processes that you're analyzing on these charts are critical to what's going to happen in the next 12 hours. Okay? Who wants to be brave enough to tackle the third one? Okay, Patrick and Al? Okay, quickly, we're running short on time, as usual.
At least we had a little bit more information to work with this time. Basically, you had a low pressure, a small low in the Oklahoma Panhandle with a dry line extending down through the Texas Panhandle, and a cold front off to the west in New Mexico, a trough extending back up towards Wyoming. The implication of the low-level moisture pattern is that there's a low-level jet advecting moisture up towards eastern Kansas and southeast Nebraska, and you've got an outflow boundary all the way in from Iowa, northern Missouri, extreme northeast Nebraska, extreme northeast Kansas and eastern Nebraska intersecting with a stationary front. And the combination of all those, we think, might continue
Thank you.
yes, initiation of deep moist convection, which could lead to flooding situations there. You also have some dew point pooling down around Childress, but there may not be any forcing mechanisms to initiate storms there. So we think that probably a heavy rain event along the outflow boundary and stationary front intersection, basically.
Good man, got a forecast built into there. That's great. Al?
All right, we see things a little bit differently. Basically, this is an AM map. It's a morning map. We've got a stationary front coming out of Wyoming along the front range of Colorado, coming down to a mesoscale low sitting in southeast Colorado, with the stationary front coming back up and lying just east of Hill City and back up to the northeast. From that, coming down, we've got a nocturnal convection from an MCC from the previous night. We've got an outflow boundary coming off the stationary front, coming into northeast Kansas and back through Missouri, with the center of the meso-alpha high sitting in northern Missouri. We've got a very sharp convergence zone or boundary setting up along that nocturnal convection boundary. We've got ongoing convection right now, which may die off, but later in the afternoon, once we pick up some heating, it may fire again. So our biggest concern right now, looking at the dew point pool coming up, is flash flooding potential with this particular scenario.
Okay. Thank you. Good job, gentlemen. Well, and the answer is? Okay. Maddox's version of reality. He's got a big old outflow boundary up here in northwest Missouri and northeast Kansas. They analyzed 2 bands of essentially moisture advection. This is analyzed as a cold front, but we now know, of course, that at least in this respect, Maddox is wrong, and this is probably a dry line if it's morning. But what if it's evening? Could it be evening?
I think there's a dry line and cold front.
Ah, okay. How can it be both?
Well, you got a dry line, and then just east of, or west of Amarillo, you have a cold front. There's a pretty strong temperature discount.
Okay, well, if it's morning, remember what dry lines look like in the morning. They look like cold fronts. Why is that? Because the cold air cools more rapidly. But then during the day, the temperature gradient reverses. So this might look like a cold front.
But it's pretty warm in drier air.
By the way, is this morning or evening?
49 and 2 area, probably more.
Okay. Okay.
50 charge.
Good suggestion, but we didn't give you one. Okay, so if this is morning, this is in effect an MCS, a mesoscale convective system. Guys drew a lot of justifiable attention to this. So if you're the duty forecaster in Kansas City or Wichita, what are you thinking about? Well, probably the Kansas City folks are worried about flash flooding. They've got that potential right in their backyard. If not with this system, perhaps with redeveloping thunderstorms that evening, if this is morning. What about Dodge City? Are you worried about anything, or are you pretty much out of the woods? You put your feet up and, start reading the Sunday paper? Let AFOS take care of itself and, send out the product, the Moss forecast, untouched by human hands? You worried about anything in Dodge City?
Locking the doors and keeping the storm.
Now, some storm chasers will kick it in, but yeah, I think you better be worried about severe weather in Dodge City. This is a fun case. There's many, many things to talk about. Here's a low on some kind of frontal boundary intersection. Let's assume this is a dry line. What do you think is going to happen with that system? Is it likely to deepen? Is it likely to fill? Is it going to move rapidly to the east or west? What do you think is going to happen?
Well, one thing I noticed is
around Texas Panhandle, Oklahoma border.
Uh-huh,
There's a return of heat moisture. You have 69 dew points.
right.
With a low-level jet, I would expect if it is a dry line, a true dry line, I mean, it should encounter some of that moisture and start to move a little slower.
I'm talking about the low-pressure system.
If this is morning, that dry line could still be retreating some.
Yeah,
And in which case, it could reset up forward movement during the day, again, another round of severe storms maybe in northwest.
so where are we going to be looking at this mesoscale low, or this, whatever it is, this front dry line intersection low? Where is that going to be if this is morning and we're thinking about the afternoon? By the way, what time of year is this?
Early summer.
How often do you get, reasonably strong thermal surges of cold air down the lee slopes late in the year? Do you think it's June? Yes. June?
Late May.
Okay. You think it's August? No. Okay, so we're talking late spring, maybe. Okay, what do you normally see in terms of the dynamics of weather systems in this time of year? Do you expect to see big, deep, powerful extratropical cyclones? Probably not. If not, we don't see any real evidence of anything, big, powerful system. What about these pressure falls that Maddox analyzed? That's a 2 millibar fall in 3 hours. Does that tell you anything about where that low is going to be moving in the next few hours?
It's going to move in the direction of their highest pressure fall.
Yeah, it's basically not going to move very far, very fast. Let's see, what about the diurnal and semi-diurnal pressure change at this time of day? If this is a rise time, then 2 millibar falls might be pretty substantial. But it doesn't appear, if this low was going to be ripping into northeast Kansas this afternoon, what do you think those pressure falls would look like? They'd be out ahead of this low, wouldn't they? And you'd have some rises behind it, possibly? Maybe some real strong rises, if this is a rise time. Okay. Well, unfortunately, my time is up. We could talk about this stuff all morning, but what I wanted to do with this exercise is give you a little sense of the kinds of questions that you as forecasters want to be asking. So I hope this has been a little bit fun, and thanks for putting up with me.
We're going to keep going here for the sake of time. I just want to make a couple of general announcements. Can you hear me okay?
What?